Part 4, Two-Dimensional Kinematics.
Two-dimensional kinematics is motion in a plane, as opposed to motion along a straight line like one-dimensional kinematics. So, for two-dimensional kinematics, we'll be talking about motion in the XY plane.
There are lots of different types of motion we can have in a plane, as opposed to motion along a straight line. We're going to discuss projectile motion, uniform circular motion, accelerated circular motion, and then rotational motion. First, let's turn to projectile motion.
Section A, projectile motion.
Projectile motion is when an object is tossed into the air. Its flight follows a curved path. Like if you push someone who's on skis and he goes over a huge jump. You can diagram his flight path like this.
The first kinematic equation we learned in one-dimensional kinematics is the same one we're going to start off with in two-dimensional kinematics. Remember the stuttering vat? We use that equation to find out an object's final velocity. We're still in the ideal world here, so we won't take into account things like air resistance.
However, since we're in a plane, we do have to worry about the x and y components of the object's velocity and acceleration.
Okay, the first two-dimensional kinematic equations we're going to look at are used for projectile motion problems. But before we can get down and dirty with these equations, though, we've got to know how to find the magnitude of a projected object, so we can use it in our equations.
Now that we're going to get into some heavy equations, we'll represent vectors in heavy, bold type. Let's say a cannonball is shot out of a cannon. The initial velocity of the cannonball makes an angle theta with the ground. Remember that velocity is a vector, so it has x and y components. And remember how we found the magnitudes of the components? Well, the magnitude of the x component of a projected object is found using the formula v sub ix equals v initial times the cosine of theta. And the magnitude of the y component is found using the formula v sub iy equals the initial velocity times the sine of theta. So these are the equations for finding the magnitudes of the x and y components of a projected object's velocity.
But before we can get gritty and grimy with the projectile motion equations, we also have to learn a special number. Just learn it, love it, and keep it in your back pocket for later. It's the acceleration due to gravity. You know, when the apple fell on Isaac Newton's head, he figured out that there must be a force that makes the apple fall down. But since this is a dramatization of actual events, we have used our artistic license to embellish a little.
The acceleration of any object due to gravity at the surface of the Earth is 9.8 meters per second squared.
Since gravity creates a force pulling an object down towards the Earth, then it is the y component of acceleration, because we've drawn the y-axis up and down. And on the y-axis, assuming up is positive and down is negative, a sub y equals negative 9.8 meters per second squared. But since we use it so much, we'll just use a little g to represent the acceleration due to gravity.
Now that we're a little more knowledgeable about gravity, it's time to get our hands dirty with the projectile motion equations.
The first projectile motion equation is easily derived from the first one-dimensional kinematic equation we learned, our old friend VVAT.
That equation is final velocity equals the initial velocity plus acceleration times time. V sub f equals v sub I plus at. For projectile motion purposes, we modify this equation to find the y component of the object's velocity. Why the y component? Well, that's the up and down component that corresponds to the acceleration due to gravity. The y component of velocity starts out positive as the object moves away from the Earth, gradually drops to 0 when it stops getting higher, and is 0 at its highest point. Then the y component of velocity gets negative as the object falls back towards the Earth. That is, the object finally falls faster and faster. So then the object's y component equals the initial positive velocity plus negative gravity, because the acceleration due to gravity goes downward times time.
So, since we're only dealing with velocity in the y direction, to get our first projectile motion equation from our VVAT equation, substitute v sub y for v sub f, v sub iy for v sub I, and negative g for a. Then we get our first projectile motion equation. V sub y equals v sub iy minus gt. Got it?
Now, the horizontal velocity stays the same during the flight because there's no acceleration in the x direction, only in the y direction. That's why in the first equation, we don't worry about the x component of velocity, because v sub x equals the initial velocity in the x direction, v sub ix, all the time. And that's our second projectile motion equation. V sub x equals v sub ix. The x component of acceleration is 0 for any object undergoing constant velocity, because the object does not speed up or slow down in the x direction. Remember, we're in the ideal world here. But in the y direction, the object goes up, slows down, stops, and then falls faster and faster. So remember, our second projectile motion equation is v sub x equals v sub ix. Got it?
The third projectile motion equation helps us find the distance that an object has traveled in the x direction. This equation deals with the position of the projected object, and it looks like this.
X final equals x initial plus the x component of the initial velocity times time, or x sub f equals x sub I plus v sub ix times t.
The fourth projectile motion equation tells us the displacement of an object in the y direction.
Y final equals y initial plus the y component of the initial velocity multiplied by time minus 1/2 gravity times time squared. Or y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared.
If you're having trouble remembering where the minus signs are in these equations, they're only in front of little g, the acceleration due to gravity.
Now that we've learned the equations for projectile motion, v sub y equals v sub iy minus gt, v sub x equals v sub ix, x sub f equals x sub I plus v sub ix times t, and y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared, we can do some problems.
Let's say bright as light, the two-dimensional Supergirl shoots a soccer ball when the ball is 1/10 of a meter above the ground. The ball is kicked at 30 meters per second at an angle of 30 degrees. The net is 20 meters away. How high will the ball be when it gets there?
The problem gives us the initial vertical position of the soccer ball, y initial, of 0.1 meters. That's how high the ball is off the ground when she kicks it. The initial velocity, v sub I, is 30 meters per second. Theta is 30 degrees. The final position of the soccer ball, x sub f, equals 20 meters, and because the goal is 20 meters away from bright as light's current position, x initial equals 0. With these numbers in place, we can find the height of the ball when it reaches the goal, which in our problem is the displacement of the y direction.
So out of the 4 equations we've got for projectile motion, only one has y in it. That's y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared. I know we don't have the time of the ball's flight, t, but we can figure that out.
Here's how we do that. We need to find time, right? So we look for an equation that we can satisfy using the information we already got, and which also has the variable time in it. The third equation, x sub f equals x sub I plus v sub ix times t, looks like our best choice. We know x final and x initial already, and we can use those to find v initial in the x direction. Once we've done that, we can solve for time. So the first thing we need to do is find the x component of the initial velocity, v sub ix.
Remember from our discussion of the components of a projected object that the x component of the initial velocity equals the initial velocity times the cosine of theta. So for our soccer problem, the initial velocity of the ball is 30 meters per second times the cosine of 30 degrees, which is the angle the ball was kicked. So the initial velocity of the ball in the x direction equals 26 meters per second.
Using our third equation, x sub f equals x sub I plus v sub ix times t, we can find time. Plug and chug, and we get that x final, 20 meters, equals x initial, 0, plus v initial, in the x direction, 26 meters per second, times time. So, 26 meters per second times t equals 20 meters. T equals 20 meters over 26 meters per second, and after we crank that out, we find out that t equals 0.77 seconds.
So we know how long the time of the ball's flight is, 0.77 seconds. It takes the ball that long to go the 20 meters to the net. But we still haven't answered our most pressing question. How high is the ball when it reaches the net? Remember, we're going to use the equation y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared to figure out that answer. So far, we've gotten y sub I, which we were given. The ball is 1/10 of a meter above the ground when it's hit. And we've got time, 0.77 seconds, which we've just figured out. Now, we need v sub iy, the vertical component of the initial velocity.
The initial velocity in the y direction, v sub iy, equals the initial velocity times the sine of theta.
The initial velocity is 30 meters per second times the sine of 30 degrees, which is 15 meters per second. So, v sub iy, the ball's initial velocity in the y direction, is 15 meters per second.
Now we have all the numbers we need to figure out the displacement of the ball as it reaches the net. All we have to do is plug and chug.
Our equation is y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared. Or in English, y final, the displacement of the ball as it reaches the net, equals y initial, which is the initial height where the ball was struck, plus the initial velocity in the y direction, 15 meters per second, times time. 0.77 seconds minus 1/2 times the acceleration of gravity, 9.8 meters per second squared, times time squared, 0.77 seconds squared. Whew! Crank that out and you get the y final. The displacement of the ball when it reaches the net is 8.7 meters. We've been saying displacement because we're talking about the change in vertical position from when the ball was kicked to when it reached the net. So basically, the ball was 8.7 meters off the ground when it made it to the net.
That's great, except that a regulation soccer goal is about 2.5 meters high, and Bright as Light just kicked the ball about 3 times that height. Field goal!
Okay, let's try another problem. Suppose Bright as Light wants to shoot an arrow just for fun at a target. She shoots the arrow at an elevation of 20 degrees. After 2 seconds, the arrow hits the target. How far from Bright as Light will the arrow be when it lands?
Remember, in the soccer ball problem, we wanted to know how high off the ground the soccer ball was. We wanted the vertical height. So that's distance in the y direction. In this example, we want to know the distance the arrow has traveled horizontally, or in the x direction.
The question is asking for the distance the arrows traveled in the x direction. So of our 4 equations, use x final equals x initial plus the initial velocity in the x direction times time.
All I know is the angle and time. You haven't told me how fast the arrow is going. How can I do this?
Calm down. We can find the velocity with a little clever figuring. Here's what we're going to do. First, we're going to figure out the initial velocity of the arrow. And then we're going to use that to help us find the initial velocity in the x direction, v sub ix. Once we have that, we'll be able to solve our problem. Okay? So here goes.
We can find the arrow's initial velocity by using our first projectile motion equation, v sub y equals v sub iy minus g times time. To get the initial velocity in the y direction, v sub iy, we have to use one of our component equations for an object in projectile motion. Remember, the initial velocity in the x direction, v sub ix, equals the initial velocity, v sub I, times the cosine of theta. And the initial velocity in the y direction, v sub iy, equals the initial velocity, v sub I, times the sine of theta.
In our equation, we have to find the initial velocity in the y direction, v sub iy, so we use the formula v sub iy equals v sub I times the sine of theta. Substituting v sub I times the sine of theta into our equation, we get that v sub y equals v sub I times the sine of theta minus gt. We were given the angle, theta, at which Bright as Light shoots the arrow as 20 degrees. We were given the total flight time, t, of 2 seconds. But the time in the y direction is 1 second, because in the absence of air resistance, it takes the same length of time for the arrow to rise as to fall.
All we have to do is plug in our numbers to solve for v sub I. Remember, v sub y is 0, because when the arrow is at its highest point, its velocity is 0. So v sub y equals v sub I times the sine of 20 degrees minus g, 9.8 meters per second squared, times t, 1 second. The initial velocity equals 9.8 meters per second over the sine of 20 degrees, which is 28.7 meters per second. So we see that bright as light shot the arrow with an initial velocity of 28.7 meters per second. See? No sweat. Now we have the initial velocity of the arrow, 28.7 meters per second.
But in order to use our equation, x sub f equals x sub I plus v sub ix times t, to find x final, the distance to the target, we need to find the initial velocity of the arrow in the x direction. Let's look at all the information we've got and figure out how we can find the initial velocity in the x direction, v sub ix. We just found out the initial velocity of the arrow, 28.7 meters per second. So, we can find out the initial velocity in the x direction by using the formula for the initial x component for velocity, v sub ix equals v sub I times the cosine of theta. So, v sub ix equals 28.7 meters per second times the cosine of 20 degrees. And you get that the initial velocity in the x direction is 27.0 meters per second. So, we've got everything that we need.
Plug, chug, and crank it. X sub f equals x sub I, which is 0 when bright as light first shoots the arrow, plus v sub ix, 27.0 meters per second, times the total time of 2 seconds. So, bright as light ends up shooting the arrow 54.0 meters before it hits the target. Wow, they don't call her the two-dimensional Supergirl for nothing.
Projectile motion is when an object is thrown into the air and its path is a curve. If faced with a projectile motion problem, first, break up the object's initial velocity into components, where v sub ix equals v sub I times the cosine of theta, and v sub iy equals v sub I times the sine of theta. Second, set up those kinematic equations. Gravity is the force pulling down on an object in the y direction. The acceleration due to gravity equals negative 9.8 meters per second squared when up is considered to be the positive y direction. The y component of a projected object's velocity, v sub y, equals v sub iy minus gt. The x component of a projected object's velocity is constant, so v sub x equals v sub ix all the time.
For the distance that a projected object has gone in the x direction, x sub f equals x sub I plus v sub ix times t. We find the displacement of a projected object in the y direction by using y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared. Finally, after we set up the equations, remember to keep your positive and negative axes the same from beginning to end. Then plug and chug and crank. And that's it.
Section B, Uniform Circular Motion.
We've learned about projectile motion. Now let's learn about uniform circular motion. That's when an object moves around a circle with a radius r at a constant velocity v, like when I swing this whistle in a circle.
The force that makes the object follow the curved path is called centripetal force, which we label F for force sub c. Centripetal means center seeking. So, the centripetal force is directed towards the center of the circle. The velocity is always perpendicular to the centripetal force. For an object in uniform circular motion, the vector of centripetal force, F sub c, is always perpendicular to the vector of velocity, v.
Because it's changing direction at a constant rate, an object moving in uniform circular motion experiences an acceleration which is constant in magnitude, and which is also directed toward the center of the circle. This type of acceleration is called the centripetal acceleration, a sub c. You can find the centripetal acceleration by dividing the velocity squared by the radius. A sub c equals v squared over r. And since v squared equals v times v, we can remember it by saying a vv over r, or aver, or aver, or aver.
Let's say Bright as Light is driving an uber mean machine around a circular track with the help of her friend. And the car's centripetal acceleration is 242 meters per second squared, and the car's velocity is 220 meters per second. What is the radius of the car's path?
Technically, at that acceleration, her guts would fall out. But this is an uber mean machine, so pretend that this acceleration won't physically affect bright as light. Let's see if our equation is of any help here.
You have the equation that the centripetal acceleration equals velocity squared over the radius. Solve for r, and you have that r equals v squared over a sub c. Plugging in the numbers for bright as light, r equals 220 meters per second quantity squared over 242 meters per second squared. Squaring 220 meters per second, we get 48,400 meters squared per second squared. Divide that by 242 meters per second squared, we get 200 meters. See how the units cancel out and we're just left with meters? Therefore, the radius of the circular path traveled by bright as light and her uber mean machine is 200 meters.
When an object is in uniform circular motion, the time in seconds it takes to complete one orbit is called its period, represented by capital T.
We all remember from geometry that the circumference of any circle is 2 pi r. When an object covers one round trip, we see that the velocity of the object is the distance the object travels, 2 pi r, divided by the period. So v equals 2 pi r over t.
Let's do an example. Suppose that the radius of the circular track is 100 meters instead. Same uber mean machine, but now the track has a different radius. Let's say her centripetal acceleration is 246 meters per second squared. Then how long does it take her to go once around the track?
The question is asking us to find how long it takes for bright as light to go around the track one time. That's the period. So, first we know we have to use the equation v equals 2 pi r over t because we have to find t, the period. But we don't have the velocity yet. So, we can use our AVER equation, a sub c equals v squared over r, to find velocity, because we have the centripetal acceleration and the radius of the track.
To find velocity, all we have to do is plug into our equation a sub c equals v squared over r. A sub c, 246 meters per second squared, equals v squared over r, 100 meters. V squared equals 24,600 meters squared per second squared. So, v equals 157 meters per second.
Now that we have the velocity of bright as light's uber mean machine, we can find the period by using our equation velocity v equals 2 times pi times the radius r over the period t.
We have v equals 2 pi r over t. Plug in the velocity v of 157 meters per second, and that equals 2 times pi times the radius r, 100 meters, and put that over the period t. Isolating t, we get that t equals 200 times pi meters over 157 meters per second. So it takes 4 seconds for bright as light to complete one orbit. That's once around the track.
Uniform circular motion occurs when an object moves around a circle with a radius r at a constant velocity v. The force that allows an object to follow this curved path is called the centripetal force, F sub c. The object's acceleration is directed toward the center of the circle and is called the centripetal acceleration, A sub c. And A sub c equals v squared over r.
The time it takes for the object to complete one orbit is the period, capital T. And the velocity of the object equals the circumference over the period. So v equals 2 pi r over capital T.
Section C, accelerated circular motion.
Uniform circular motion happens when an object moves around the circle at a constant speed. Accelerated circular motion happens when an object moving around a circle changes the magnitude of its velocity.
This type of acceleration is called tangential acceleration, a sub t. Tangential acceleration is always in the direction that the object is moving and is always tangent to the circle. So the vector of tangential acceleration, a sub t, is always tangent to the circle.
The tangential acceleration is positive if the object's velocity increases, and negative if the object's velocity decreases. The total acceleration of the object is the vector sum of the tangential acceleration and the centripetal acceleration. Remember, that we can't add vectors using the regular old way. To find the magnitude of the vector sum, use the Pythagorean theorem.
Let's do an example of accelerated circular motion. Bright as light's cat, named Cat, enjoys chasing her tail. Her head moves in a circle with non-uniform acceleration.
Her head's total acceleration is 27 centimeters per second squared. The radius of the circle is 15 centimeters, and the velocity of Cat's head at the start is 12 centimeters per second. Find the tangential acceleration. Notice that everything we've been given is in centimeters, but acceleration is measured in meters per second squared. So in order to make our equation work, we need to convert our information from centimeters to meters.
Remember, 100 centimeters equal 1 meter. To convert centimeters to meters, we multiply the acceleration, 27 centimeters per second squared, times 1 meter over 100 centimeters, which equals 0.27 meters per second squared. And now, converting the radius and velocity, the radius equals 0.15 meters, and the initial velocity equals 0.12 meters per second.
Now that we got that covered, we know that A equals A sub t plus A sub c. We know what A is. We were given that in the problem. The head's total acceleration is 0.27 meters per second squared. The question asks us for tangential acceleration, A sub t. So let's find A sub c so we can figure this puppy, kitty, out.
Remember, we just showed you the equation for finding centripetal acceleration. A sub c equals v squared over r. Ever. A sub c equals v squared, 0.12 meters per second squared, over r, 0.15 meters. Dividing this out, we get that the centripetal acceleration equals 0.1 meters per second squared.
Now that we have A sub c and the total acceleration, we can use our equation to find the tangential acceleration. But realize that acceleration is a vector quantity, and we can't just use regular addition here. But lucky for us, we can use the Pythagorean theorem, because we can connect the vectors and make a right triangle to get the vectors' magnitudes. Of course, we're not going to draw the vectors because our standard deviant graphic artist is on a break. We're just trying to explain why we can use the Pythagorean theorem. Since vector A equals vector A sub t plus vector A sub c, the magnitude of A squared equals the magnitude of A sub t squared plus the magnitude of A sub c squared.
Using algebra to isolate A sub t squared, we get A sub t squared equals A squared minus A sub c squared. Now we can plug and chug.
A sub t squared equals 0.27 meters per second squared, quantity squared, minus 0.1 meters per second squared, quantity squared, which is 0.06 meters squared per second to the fourth. Take the square root of that to find A sub t, and we get that the tangential acceleration of Cat's head is 0.24 meters per second squared. And because the tangential acceleration is positive, we know that Cat's head is going faster and faster and faster and faster and faster.
Accelerated motion in the circle occurs when an object's velocity changes its magnitude. This type of acceleration is called tangential acceleration, A sub t. There are a few things we should know about tangential acceleration.
First, tangential acceleration is always tangent to the circle. Second, when an object's velocity increases, A sub t is positive. Third, when the velocity decreases, A sub t is negative. And finally, the total acceleration of an object in accelerated circular motion equals the vector sum of the tangential acceleration and the centripetal acceleration, or A equals A sub t plus A sub c.
Circular motion, no problem, right? Now let's move on to rotational motion.
Section D, rotational motion.
All right, we've learned about objects that move in a circle. Now let's talk about rotational motion, objects that rotate about an axis. Think of an object that rotates, like a planet.
Rotating objects are described by the angle through which they rotate, theta. With the equations we'll learn in this section, we must use radians, represented by RAD, instead of degrees. So it's important to remember that when doing calculations with objects that rotate. Here's how we find the radian measurement of a circle.
If you have a circle with radius r and an arc of that circle s, then the angle in radians is the ratio of the arc divided by the radius. So the angle theta in radians equals S over R.
There are 360 degrees in a circle, and pi radians equals 180 degrees. So whenever we need to convert degrees into radians, or vice versa, use the ratio pi radians to 180 degrees.
But here's the tricky part. Radians are weird because they have no dimensions since they're defined by the ratio of two lengths. So when doing calculations with them, the rad part always drops out in the end, unless your answer is an angle that's supposed to be in radians.
Suppose you want to convert 270 degrees into radians.
Just multiply 270 degrees times pi radians divided by 180 degrees, and you get 4.7 radians.
But you said to dump those rads.
Only when you're not dealing in an angular quantity. A radian is an angular quantity, so keep it.
Keep me!
Say the largest part of a little circle has a diameter of 0.04 meters. If we put a point on the edge of the circle here, and the circle turns through an angle of 30 degrees, how far does the point on the edge of the circle travel?
How far does it travel? We didn't learn the equation for that.
Actually, we did. There's a point going around in a circle. Whatever distance that point covers is the arc of the circle S.
Oh, okay. So we can use the equation theta equals S over R.
Right, but first we have to find the radius of the circle.
We were given the diameter d of the circle as 0.04 meters. Well, the diameter of a circle is twice the radius. So the radius equals the diameter, 0.04 meters, divided by 2, which is 0.02 meters.
All right, so we've solved for r and we got theta. All we have to do is plug in and solve for s in the equation theta equals s over r, right? Wrong. Remember that we can only use radians when using rotational motion equations.
So, because we were given theta in degrees, we have to convert degrees into radians in order to use our equation. So we have 30 degrees. Multiply that by pi radians over 180 degrees, and you get that 30 degrees equals 0.52 radians.
Now we can plug those numbers into the equation theta equals S over R. We're solving for S, so switch the equation around to get S equals R times theta. S equals 0.02 meters times 0.52 radians. Multiply and S equals 0.01, which means that the point on the edge of the circle traveled 0.01 meters.
So now we know how to find the distance a point on a rotating object travels when we use angles and radians. Now let's learn about the angular velocity of a rotating object. Don't worry, you'll like it.
The angular velocity of a rotating object, represented by the Greek letter little omega, is the angle theta, through which it turns over the time t it takes the object to turn. So, angular velocity has the unit of radians per second.
For example, if it takes 2 seconds for the little globe to turn through 25.2 radians, the angular velocity would be 25.2 radians over 2 seconds, or 12.6 radians per second.
If an object is moving with uniform speed, v, in a circle with radius r, then the distance, s, that the object travels is v times t. So let's see what we can do with this information.
Theta equals S over R. We showed you that equation a while ago. We also know that S equals VT. If we substitute VT for S, theta equals VT over R. Now, dividing both sides by t, we have theta over t equals V over R, because the t's cancel on the right. Okay, are you with us so far? Theta over t equals V over R. We just showed you the equation for angular velocity. Omega equals theta over t. So, if omega equals theta over t and theta over t equals V over R, another way of writing angular velocity is omega equals V over R.
This equation is usually rearranged and written as v equals omega times r, where v is the linear speed of a point on an object going around in a circle, omega is the angular velocity, and r is the radius of the object's path.
This equation is especially useful when speaking about a point that's a certain distance from the axis of rotation.
The axis of rotation is the axis about which all the objects of the rotating body are moving. For example, this is the axis of rotation of Earth, and the Earth is spinning about this axis.
In the equation v equals omega times r, v is directly proportional to r, because if the velocity increases, the radius will increase, and if the velocity decreases, the radius will decrease. So the farther a point on the object is from the axis, and the greater that point's radius, then the greater its linear speed.
Let's test this out. Let's find the linear speed, v, of a point on the little globe that's 0.005 meters from the axis when the globe is spinning at 7 radians per second.
Well, we're given the radius, r, of the point from the axis of rotation, 0.005 meters, and the angular velocity, omega, 7 radians per second. Plugging that into our equation of v equals omega times r, we get the linear speed of that point to be 0.035 meters per second.
Now compare that to a point that is farther away from the axis of rotation. Say there's a point that is 0.02 meters away from the axis of rotation, with the same angular velocity of 7 radians per second.
The linear speed equals the angular velocity, 7 radians per second, times the radius of 0.02 meters. And we get that v equals 0.14 meters per second.
Comparing this linear speed with that of the previous speed of 0.035 meters per second, we find that 0.14 meters per second is 4 times faster than when the point was closer to the axis of rotation. And that's because we're 4 times farther from the axis of rotation. So, if a point is 5 times farther from the axis of rotation, then the linear speed will be 5 times faster.
When an object rotates about an axis, that's called rotational motion. An object rotates through an angle, theta. Theta is measured in radians instead of degrees in rotational motion problems. There are pi radians in 180 degrees. In a circle with radius r and an arc s, theta in radians equals s over r.
The angular velocity of a rotating object, lowercase omega, is the angle through which it turns over the time it takes to turn, or omega equals theta over t. The linear speed of an object is directly proportional to how far the object is from the axis of rotation, the axis about which all objects are moving. This relationship is written as v equals omega times r.